Alright, so welcome back. Now we're going to talk about these standing waves within the fractal cosmos. Each one of these stratum particles is a standing wave. The wave of this particle extends out to the radius of the universe. So every atom in our universe is actually as big as our whole universe. If you can imagine that, it's quite a staggering concept. However, the most interesting part of the atom is the core. So we can treat these atoms as little balls with cores whose radius is on the order of nuclear dimensions, 10 to the minus 15, 10 to the minus 18 meters. Okay, so if you were to plot the pressure around an atom in terms of the pressure in the substrate on which that atom is a standing wave, you'd find near the core a sombrero type plot of pressure versus radius. So when you're right at the center of the atom, you're going to have the maximum pressure. And as you move out to the radius of the core, you're going to hit a node. You move out 2 more radii, and you hit another node. 2 more radii, another node. So what you have are concentric shells. Every 2R, there's a node. So there's shell, 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 going out to the distance of the universe. Now, in each shell, the energy is the same because it exactly balances out the energy in its neighboring shells. But, as you know, the volume is getting larger as you go out. It's a 1 over r squared drop in volume of the shell. If we were talking about volume of the whole sphere, it would be 1 over r cubed. But the shell is 1 over r squared, which gives us the inverse square law of many of our forces of interaction: electrical, potential, gravity. As we know, it drops off with 1 over r squared. That's nothing too profound, but that is related to the pressure surrounding the core. Now this pressure obviously doesn't stay like that. That would not be very stable. This atom is continually vibrating at a frequency, many orders of magnitude higher than what we consider frequencies of light, X-ray, gamma ray. This atom is really cooking. It's going at 10 to the 23rd vibrations per second. Okay, that's probably almost a trillion times a second. This atom vibrates where the maximum pressure drops to the lowest pressure, which would be 0 actually. So we have 0 down here. This is 0. And then it goes back up again, trillion times a second. And likewise, the neighboring shell, when this is going down, that one's going up. So really what's happening is the particles are moving out and colliding. Particles from here are moving in, particles from here are moving out, they collide, they bounce back. But actually what's happening is there's a wave coming in, and there's a wave, it bounces at the center and it goes out. So these 2 waves form a standing wave. This is common knowledge in the wave theory, that's how you form a standing wave. You have 2 waves of the same frequency moving in opposite directions, and you end up with these nodes in a standing wave. So there you have a nice simple model of a particle as a pressure wave, and the pressure times the volume is the energy. You could compute the energy for the core and then the energy for each consecutive shell going out to the distance of the universe. And next episode I'll describe what this maximum pressure is and why it's important. Thank you very much.